Hello all. Today we'll be talking about an important topic in electrical engineering, that is phasors. We often see that an AC voltage or current can be represented by a vector VA, but in reality are actually sinusoids. So, how the sinusoidal electrical signals, in this case voltage, is represented by a vector. We also often see that a three-phase balance circuit, the complex waves are represented by three vectors which are 120-degree apart from each other. So these complex voltages such as VA, VB and VC, how they can be represented by these three vectors VA, VB and VC. In polar diagrams, they are 120-degree apart, like plus 180 degree and minus 120 degree. So, how they are actually equivalent? In the first part, we will talk about this. To see that, why is that equivalent? Why the translation is true? We assume that a particle is rotating anticlockwise in a circular path, like this way. So, suppose we start a stopwatch when it is at the angle 0. Now at the time t1 it is in this position, so the projection on the y-axis will be at this point. Similarly, with respect to time, when it rotates further, we can also draw its path like this. So when it completes all the way and be at the angle 2 pi or 0, it becomes 0 again, and it completes some one circle and we get a one complete sinusoid. Suppose now we start the stopwatch not at the 0 point, but for some reason we start the stopwatch when it's 120-degree lagging from the x-axis. Now what happens? To see that it's rotating in the same direction, so the projection on y-axis at time t0 will be in this point. So with respect to time, when it goes further, it goes down and hit the lower, and then it rises again to the 0. And similarly, you can see that when it goes around one circle, it completes one cycle as well. uh, Similarly, in the same fashion, we can say that if we heat the stopwatch when the particle is at 120-degree farther from the x-axis, that is leading from x-axis, we can draw the similar sinusoidal curve, which will have a very different initial point than other two at t equals to 0 or time t equals to 0. It will also complete a one circle uh, when the particle moves along, and it will complete a one circle in sinusoid as well. So this is the basic of three-phase voltages or currents or any electrical signals. This is known as for this figure, this is known as the phase angle, the initial phase angle, which is 120-degree. For this figure it's 0 degree, and for this figure the initial phase angle is plus 120 degrees, so 120 degree. So now if you look into these figures, also we have to remember that the radius of the particle that is moving also uh, changes the height of the sinusoid. So now if we look into three particles, rotating particles on the same path, one which is the particle A, at time t equals to 0 we start its stopwatch and it will be in this sinusoidal way, and for this particle the y-axis projection will be a little bit different, so it will be something like this. which is being drawn by the red curve here. Now for this particle, it's a white particle now, so the path or the projection on y-axis will be like this sinusoids. So this is why the three phase of voltage or current like A, B and C, uh, these complex sinusoids can be represented by these three vectors. So this is the reason, and if these three particles rotates in a same angular velocity, which is omega, and in the same direction, then with respect to the first particle or the initial particle, we can say that the angular difference between these three particles will always be constant, and for a balanced circuit we all know that the angle will be 120 degrees. So that's why a complex vector, that's why a complex wave can be represented by a vectors. So now if we assume an electrical circuit, uh, suppose we have 2 points A and B, which is being connected by this impedance. uh, this impedance here uh, is connected between point A and B. The voltage between these 2 points is VAB. The current flowing through the circuit is denoted by IAB. Since uh, this impedance is R plus JXL, uh, this is a lagging impedance, so it has a lagging power factor. So we all know that if we represent the VAB and IAB will be lagging by the angle of power factor. So now you can easily understand why this is equivalent to the complex sinusoids. So if we want to draw the sinusoids, it will be something like this. So the VAB, the sinusoids of VAB will start at 0, but the sinusoids of IAB will not be at the 0. To draw it more, if you look into there, it will start not at the 0 but below the 0, and it will try to follow the VAB but with a lagging angle. So this IAB is lagging by the same power factor theta. This current or voltage IAB is actually a complex sinusoid, but rather than computing and evaluating all the things in complex sinusoids, it's very easy to represent all this in a vector, and this vector representation is actually equivalent, and we can name them as a phasor for calculation. So in the first part we talked about the phasor, then next we will talk about the calculations.